Okay, so I realized that when I was lecturing this in class, it did not record. So I'm gonna redo the lecture. Okay, move this out of the way. Here we go. Oh, no, move myself out. Okay, this section deals with molecular geometry. And so I'm going to explain what Vespr is and how it applies to shapes of molecules, and then predict, well, show you a table that will help you predict the shapes. So you'll have to do some Lewis structures as well. And we'll talk about forces another day. But this is going to set you up for your activity for the next 2 days. So molecular geometry is really important because shape of a molecule does affect the property of that compound that you're looking at. So not only does it depend on the shape, but it also depends on the bonds. So we've been discussing ionic bonds and covalent bonds as well as metallic bonds and how they relate to their properties, where like ionic bonds are brittle and they break easily. And metallic bonds, because of the sea of electrons, you can, they're malleable, they're ductile, they're great conductors. Covalent bonds have a low melting point. So those are all properties based on types of bonds, but we also have to take into consideration the shape of a molecule. And so when you just look at a chemical formula like H2O, that doesn't tell you much about the polarity as well as the shape of it. If you wanted to figure out polarity, you could look at electronegativity values and do some math to figure out, is it nonpolar or polar? But it doesn't tell you much. And so Vespr theory, what it tries to show us is what's the most likely shape of this compound, and how does that shape affect its properties? So the theory we're looking at today is called the Vespr theory, and it deals with valence electrons and how they want to be as far away as from each other as possible, because we have this repulsion force going on here. So by definition, repulsion between sets of valence level electrons surrounding an atom causes these sets to be orientated as far apart as possible. And so Vespr literally stands for valence shell electron pair repulsion. So you're going to need your little model kit, and I'm hoping this is like recording my face as well somewhere on the screen, but I'll just put it up there. I don't know. I hope it is. Okay, so the first shape I want to talk about is called linear shape. And there are two ways that linear shape can result. First off, if you just have a compound, and that's a typo, it really should say compound or a molecule, that only has two atoms, the only shape that it can be is linear. And so in your little molecule ball and stick model kit, find two yellows and a wooden peg and create a linear shape. Here I have atom 1, atom 2, this is hydrogen, the same colored ball. And so here we go. You can make hydrogen chloride, okay? The yellow with a green. Hydrogen chloride. This would be the hydrogen, this is the chlorine, okay? So when you just have two atoms, the only shape it can be is linear. Now, another way that linear can result kind of deals with beryllium, and we don't have a ball that represents beryllium, but it would be something with two holes on either side of it, and it's AB2. So you have two atoms bonded to the central. There's no lone pairs on the central atom. And so a great example, beryllium fluoride. So there's my beryllium with two fluorines attached to the side. Okay, a second shape is called trigonal planar. So the simplified chemical formula for that is A and then B3. So you have a central atom with three atoms bonded to it. I don't know if my face is covering that up. So three atoms bonded to it. There are no lone pairs on this central atom. So when you draw like the Lewis structure of it, you don't see any pairs of dots around it. Now these three AB bonds, they want to stay as far apart as possible away from each other. And as a result, you end up with this equilateral triangle. 120 degrees is the maximum distance between all of them. So if your kit has a dark colored ball, it's got to be a dark colored ball, you can show trigonal planar. So I have one. I don't know if I put one in your kit. So if not, I will apologize, and you'll just have to, I'll just have to use my imagination when you do your lab. Okay, so hold on here. Okay, so I got my dark colored ball with the 3 wooden pegs, and chlorine is usually the color green. Yes, and we have this 2 greens crumbs. So I'm going to use yellow. Chlorine is usually green. Yellow is usually hydrogen, but we'll just use our imaginations that these are green. So it's called trigonal planar because, okay, here's my equilateral triangle, but if I flip it onto the side, all of those atoms are in the same plane. They're flat. Okay, so equilateral triangle this way, but then flat this way. So I'll show you. Here's the cartoon. 3D ball and stick. Here's the Lewis structure of that. And you can kind of see that all of these bonds are 120 degrees away from each other. Okay, third shape, bent or angular. So there are 2 ways that you can create a bent or angular molecule. And the first way is AB2E. Now this E stands for a lone pair on that central atom. So here we're going to have 2 atoms bonded to a central atom, which is A, and one lone pair on that central atom. So find a dark colored ball or a blue ball or whatever shade of blue I gave you. Okay, that's going to be in the center, and then you need a green and a red, which you should have. Okay. Yep. Sorry. Yeah, it's a double bond. Shoots. Okay, so in this kit, I need you to find 2 springs. When you draw the Lewis structure for this one, there is a double bond between the nitrogen and the oxygen. And so the springs are used to show double bonds. So you stick the 2 springs, and sometimes you kind of have to twist it in there. Here are the 2 springs, and then you're going to attach 2 springs to the opening of the red ball to form your double bond. And I grabbed yellow, so I'm going to for green to represent the fluorine. Okay, so here I have that double bond with the oxygen, and this is my nitrogen, and this is the fluorine. So I'll show you that. So there it is. You can see that it's bent. Now, bent shape is actually pretty important because this usually means that the molecule is polar. I can cut this molecule in half and get some polarity. You know, maybe the nitrogen has a, I don't know, a more positive charge than these 2, and these are negative. So I can get this polarity. And polarity just means that it's like a magnet. You have a slightly positive end and a slightly negative end. And because of that, it can be attracted to other molecules. Okay, so water is a great example of this. Again, water is H2O, and here's my oxygen, my red. And you can see that the red ball only has 2 holes. If you right, 2 wooden pegs, and here are my 2 hydrogens. You can see that it is also bent, and water is polar. Oxygen tends to be slightly negative, and hydrogens tend to be slightly positive, and I can cut this molecule in half. And if I take a look at water, you can see that it is bent. So AB2, here's my A, these are the 2 B's, and then the E2 stands for the 2 lone pairs, and they kind of act like imaginary bonds that are pressing down on these 2 hydrogens to make it bent. Okay, a third shape, and probably the simplest, I think in my personal opinion, is the tetrahedral. And that is when you have a central atom and you have 4 atoms bonded to that central atom. And so black does have 4 holes in it, and it does form a tetrahedral. Black is usually represented identifying the black ball and 4 wooden pegs and 4 yellows to represent hydrogen. We'll make some methane here. So the simplified equation is A with 4 B's. Okay, 1, 2, 3, 4. But you can set it down, and kind of looks like a pyramid, if you will. But you can see methane, perfect example of tetrahedral. 4 atoms bonded to the central atom. Okay, trigonal pyramidal. You're going to need that dark colored blue ball again. And if you don't have it, I do apologize. You could just take the top off. This is still trigonal pyramidal. So if you don't have a blue ball, black would work too. But it's A and then B3. There's my 3 B's, 1, 2, 3. But when I look at it, it's like a tripod. Trigonal pyramidal, it's like a tripod. But I'm going to show you a black ball or blue ball here. Trigonal pyramidal. It's just with the blue ball. Okay. So, all right. So what's going on here with the Lewis structure? Here's my nitrogen and the 3 hydrogens, and you can see that the nitrogen has a lone pair here. And so you just have to imagine that there's a lone pair here, and it's pressing down on those hydrogens. Could you say that this molecule could be polar? Yeah, you could cut this molecule in half and get a positive end and a negative end. All right, the third shape is trigonal pyramidal, and you need a teal colored ball. I'm going to grab it real quick. Sorry, thought I grabbed it. So this colored ball. So that's going to be your central. That's going to be the phosphorus. And I don't have 5 greens, so you can use yellow. 85. Otherwise, just again, use your imagination. 1, 2, 3. Oh boy. Okay, for some reason it's kind of loose. I don't know why that one hole is loose. But okay, it's not perfect. Okay. But here's that color, light color blue, my phosphorus, and I have 5 atoms bonded to it. Maybe if I just do this. Solved. Use a longer peg. Okay, so 1, 2, 3, 4, 5. Okay, now it's not perfect because these 3 right here are supposed to be flat. They're supposed to be in the same plane. So you can kind of see that in this picture here where they're supposed to be in the same plane. You get that trigonal planar going on with a north pole and a south pole. Yeah, well, our kits don't do that, but this is as close as it's going to get. So AB5. Okay, octahedral, we can't construct an octahedral with our kits, but it's 86. You have 6 atoms bonded to it. And so with sulfur fluoride, here we get 4 coming off of it and a north and a south. So you form a square in the center here instead of an equilateral triangle, and then a north pole and a south pole. Now, if I were to just give you, a compound and say, okay, figure out the shape of it, you might struggle trying to, well, how do I do that? So this table is going to help you. So I don't know if you want to screenshot this table. This table is going to come in handy when you do your lab activity. So how it works is it's got the shapes here, okay? And it has a 3D or picture of that shape. And then these two columns are probably the most important. Atoms bonded to the central atom, and then lone pairs of electrons. And what it means by lone pairs of electrons to the central atom, okay? So, for example, let's do some examples. So on the next slide here, I have CO2, okay? So the first thing you want to do is you want to draw a Lewis structure. So carbon has 4 valence electrons, right? And oxygen, well, there's 2 of them at 6. So 2 times 6 is 12, plus 4 is 16. So I have 16 valence electrons, right? So carbon is usually black and oxygen is usually red. But when I draw the Lewis structure here, I have carbon as my central atom, and then I'm going to bond 2 oxygens to it. And then you're going to go in and fill in all the lone pairs because everything needs to have an octet, right? Now carbon has 8. Now this oxygen has 8, and the other oxygen has 8. Now I'm going to count up all the electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Well, geez, I'm only supposed to have 16. So that means we're going to have some multiple bonds going on here, right? So you erase a lone pair. It's a really big eraser. And you form a double bond. All right, now let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18. Shoots, we still overshot. So I'm going to take a lone pair off the carbon again and add oxygen, because oxygen can't form a triple bond, and form another multiple bond here. 2, 4, 6, 8, 10, 12, 14, 16. Hey, there it is. Okay, so now I need to construct this, right? Now, I could just, construct it like, okay, I know I'm supposed to have two bonds here, or 2 double bonds, but go back to your table, okay? How many atoms are bonded to the central atom? All right, 1, 2. So it could be linear, bent, or bent. Now you can take a look at the next column. How many lone pairs of electrons are on the central atom? So you'd look, oh, 0. So I'm looking for a 0. There it is, 2, 0. So this shape is going to be linear. And then to prove it, you would actually construct it, okay? So here's my carbon, and I'm going to find 4 springs. All right, here's my 4 springs. Twist some of them in there, hopefully they stay, and hopefully I am able to construct this without losing an eyeball. Sometimes these springs can be ticking time bombs, and yeah, I don't know if I'm gonna be able to do it, but we will attempt. It's not looking so great. Liquid spring. I think that was part of the problem. I had a really bad spring. But then you're probably thinking, oh yeah, right, Mrs. Erickson. Blame it on the spring. Spring does matter in this case. Okay, I think I'm gonna get it. There it is. I don't know how well it will hold. It's probably gonna fly off, but it's linear. 2 double bonds. There's my carbon, my 2 oxygens, and it is in a flat plane for linear. So that's kind of what you're going to be doing for your lab tomorrow. Okay. Let's take a look at chlorine 3 minus. So chlorine has 7, and we have 3 oxygens at 6 each. So 3 times 6, sorry. And then that minus charge means you're going to add 1. Add 1, and we get a total of, all right, so we have 18. 18 plus 7 is 25, 26. We have 26 valence electrons. Okay, now Chlorine can only form one bond here. Okay, so that means my oxygen is probably going to be a central atom, and oxygen's kind of going to break the rules here a little bit. But here, my chlorine, and just going to throw oxygen around it. Bivalent pairs. Oops, should have stopped me. I have too many oxygens. Got carried away. It's only 3 oxygens. Okay, continue, resume. All right. Everything has an octet now. But do I have 26 valence electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay. So now I'm going to use my handy dandy table on the previous slide. How many atoms are bonded to the central atom? It's 3, right? I got a chlorine and 2 oxygens. So it could be trigonal planar. Whoops, way to cover up that 3. Or trigonal pyramidal. Now we got to take a look at the second column. How many lone pairs of electrons are on the central atom? In this case, 1. So looking for a 3, 1. There it is. Okay, it's going to be trigonal pyramidal. Now, oxygen is usually red. I think I had this. Yeah, is usually red, but then I just realized that the red ball only has 2 holes in it, so you can't use red. So go ahead and use black. Okay, and we're going to have more black punched off of it. So black is going to represent oxygen. And then chlorine is usually green. You can see that it is trigonal pyramidal, right? Go to the previous slide, trigonal pyramidal. Okay, it's kind of like a tripod. So it works, okay? So I do have a short little video here. Share a different screen. There it is. Hold on. Let me turn my Bluetooth off. Kids.
The atoms attached to a central atom spread out from each other as much as possible. But how does this model explain the geometries of molecules with non-bonding electron pairs? The nitrogen atom in an ammonia molecule has 1 non-bonding pair of electrons. These electrons also repel the adjacent atoms and do so even more strongly. The atoms, therefore, are pushed closer to one another. We can predict the geometries of molecules by considering the locations of all the electron pairs in the valence shell. Phosphorus trichloride, for example, is made up of a central phosphorus atom attached to 3 chlorine atoms by single bonds. Consulting the periodic table, we see that phosphorus has 2 valence electrons in s orbitals and 3 valence electrons in p orbitals. The chlorine atoms all have 7 valence electrons, 1 empty spot in one of their p orbitals. So each of the single p orbitals in phosphorus must be bonded with the single p orbitals in chlorine, leaving a lone pair of electrons on one side of phosphorus. According to our model, the geometry of phosphorus trichloride, therefore, is not trigonal planar, but rather trigonal pyramidal, with the chlorine atoms bent away from the lone electron pair. The atoms attached to a central atom spread out from each other as much as possible. But how does this model explain the geometry?
Okay, I think I played. It just seemed way short.
The atoms attached to a central atom spread out from each other as much as possible. But how does this model explain the geometries of molecules with non-bonding electron pairs? The nitrogen atom in an ammonia molecule has 1 non-bonding pair of electrons.
Yeah, okay, sorry. I'm sorry. I just wanted to make sure. Anyways, So I guess I've been saying pyramidal wrong. It's pyramidal, but you get the gist. So your lab tomorrow, your activity tomorrow, and I guess I can just show it right here. Share screen again. Log into Google Classroom. So tomorrow it's going to post. Okay, so here's the. Okay, so it's going to be titled Vespr Model Lab. Okay, and you're probably going to have to open it in Notability and do it in Notability because you're going to be taking some pictures to prove that you actually constructed it. So it says for each molecule below, you want to draw the Lewis structure, then construct the model using the model kit. And you're going to take a picture and include a key, okay? And then name the shape of that molecule. So you're doing 4 things. You're going to draw the Lewis structure. From the Lewis structure, you're going to revert back to this handy dandy table that was in the PowerPoint. I guess I can show you that one more time. You're going to revert back to this table, okay? Figure out how many atoms are bound to the central atom and then do the lone pairs of electrons. And then construct it using the model kit. Oh, I just dropped a ball. Using the model kit I gave you. And if that's why I say use a key. You need to make a key for the colors and elements. So if black is carbon, then you just do like a black dot equals carbon. Or if yellow is hydrogen, a yellow dot equals hydrogen. And then you're going to name the shape. Is it linear? Is it bent? Yeah, I'm just going to quickly see if I have any. I cleaned out my mailbox a long time ago, this past summer, I should say. So I'm curious to see if I have any examples of this because I had them email it to me. So cancel Vespr. Well, maybe not. But anyways, I believe there's 12. So this is going to be worth a lot of points, okay? Because you're basically getting 4 points for each molecule, okay? Okay, so that's what we're going to be working on for the next 2 days. And it doesn't look like there were anything emailed to me, unless the internet has. Oh. Yes, yeah. So they took a picture, and then they did the key, and then there's the shape. And I'm not going to show you the second page, so you can't cheat. All right, so that does it for chemistry. I hope this was helpful. Yeah.